Swayam Prabha. Digital India. Educated India.
Lighting ठीक है. Last time we were trying to design a space heating system in Srinagar, and the space heating load has been calculated as in problem number 6, 18.4 gigajoules in a month, and the degree days we have calculated for the month of December as 533 for December. This is from problem 6. So, 7 the collector properties are FR UL is 2.63 watts per meter square degree C, FR tau alpha normal is 0.72 with tau alpha bar upon tau alpha n 0.94, calculated by the detailed method we have described in the earlier problem while dealing with phi bar of chart method. So, that FR tau alpha bar will be the product of these two equal to 0.6768. Then the data is monthly average daily radiation is 6.99 megajoules per meter square day, and the diffuse radiation is 4.99. So, you can understand it is a cloudy day, and the mean declination for the month of December is minus 23.0 degrees. So, with this you have got the direct radiation H b bar as H bar minus H d bar equal to 2 megajoules per meter square day. So, first our task will be to compute the solar radiation received by the surface, and for that I need the sunset hour angle omega s is cos inverse minus tan phi tan delta, which is we calculated 73.37 degrees, and omega s dashed for the tilted surface is the minimum of 73.37 and cosine inverse minus tan phi minus beta tan delta. We have the trigonometric argument. When delta is negative, this minimum will turn out to be 73.37 in the northern hemisphere. So, now the tilt factor for beam radiation R b bar is the familiar formula cos phi minus beta cos delta cos omega plus R b bar, this should be sin omega s dashed plus sin phi minus beta sin delta omega s dashed into pi by 180 upon the cos theta z, that is zenith angle, cos phi cos delta sin omega s plus sin phi sin delta into omega s into pi by 180, which turns out to be 2.18. So, R b bar for this situation is 2.18, and your R bar for the entire radiation. If you have H T bar equal to, we actually do not need this, except later on we may, R B bar H B bar, which is R bar H bar for the sake of completeness, plus H D bar times 1 plus cos beta by 2. You recall all the formulae we derived earlier are being used in these few examples that we are doing as application of V bar F chart method or the F chart method. So, this will be 2.18 into 2 megajoules plus 4.99 into 1 plus cos 50 degrees, that is the beta, by 2 plus 0.2 into 1 minus cos 50 by 2 into 6.99. That turns out to be 8.69 megajoules per meter squared day. This is the solar radiation falling on the collector surface in the month of December, the average daily value. So, now the F chart variable x is the non-dimensional collector loss. X is F R U L times 100 minus ambient temperature average multiplied by AC into number of seconds in the month by the load on the system. And since the storage is considered to be different, you have got x c by x is actual by standard to the power minus 0.25. Let me just check up. It tank is 125 liters per meter square. Okay, actual storage is 125 liters per meter square compared to standard of 75 liters per meter square. So, we need to correct the variable x as we have done here. So, first x will be 2.63 into 100 minus 2.8, which we have calculated while calculating the degree days, the average temperature times 50 times 24 into 31 into 3600 by 18.4 into 10 to the power 9 joules. This will be 1.86. So, x c will be 1.86 times 125 by 75 to the power minus 0.25, which will be equal to 1.64. So, larger storage leads to a smaller x c, which basically means a lesser loss and hence a higher solar load fraction, which can be easily understood because we have got a larger storage. So, there will be more storage. So, y is F r tau alpha bar times H t bar A c into the number of days in the month by the load, which will be equal to 0.6768 times H t bar is 8.69 megajoules multiplied by 50 times 31 into 10 to the power 6, that makes it joules, by 18.4 into 10 to the power 9, that makes the load also in joules. Which gives your y as 0.495. So, I use the correlation for the liquid based F chart 1.029 y minus 0.065 x. Now, I will directly write the x c because I have already corrected, minus 0.245 y squared plus 0.0018 x c square plus 0.215 y cube. So, this comes to be 0.3732. So, useful energy delivered by the solar energy system to meet the load will be the solar load fraction times L, that will be 0.3732 times 18.4, that will be equal to 6.86 gigajoules. Okay. So, this is the F chart method. Only variation is that we said that the standard storage is 75 liters. Instead of that, we have an actual storage of 125 liters per meter square of the collector area. So, the variable x has been corrected accordingly, and we applied the F chart correlation that required the calculation of y, which required basically h t bar out of the ones to be computed. Rest of them are all more or less known to us. So, you have got 6.86 of the kilojoules met out of the 18.4 gigajoules by the system of square meters 50 square meters. Now, problem 8 is a slight variation. If standard flow rate and standard storage have been employed for the same FRUL and FR tau alpha bar as calculated, and what will be the F? Let me just check up. Right, what will be the solar load fraction if air based collectors with standard flow rate have been employed with standard storage and assume FRUL is equal to so much and FR tau alpha. So, second one is, if I use air based collectors and standard storage, what is the standard storage? A 0.25 meter cube per meter square of the pebbles, and then standard flow rate. What is the standard flow rate? 10 liters per second per meter square under NTP. So, these are numbers I am repeating so that you will be remembering, and when once you say standard storage and standard flow rate, you must almost be able to know what they are. X and y do not change. Of course, it is also given FRUL is same 2.63 watts per meter square degree C. FR tau alpha normal is 0.72 and tau alpha bar by tau alpha normal is 0.94, and which were then x is 1.86, the previous number uncorrected because these are standard storage and standard flow rates. Y is equal to 0.495. So, this is only just to show if an air based system with collector parameters being similar values, same values as 2.63 and 0.72 are equal to that of the liquid system, what will be the difference in the solar load fraction. That in a way explains the superiority or otherwise of your air based system versus the liquid based system. in addition to other advantages or disadvantages like pumping power being higher for a air based system, etc. So, F is a slightly different expression. So, I will write it as F air. So, that you will know that this is for the air based system minus 0.065 x minus 0.159 y squared plus 0.00187 x squared. Just there are differences in the sign compared to the liquid based system that you can note, the numbers are more or less comparable. The major difference to be tackled or understood is that whether a equivalent cost air based collector will have same FRUL and FR tau alpha as that of the liquid based collector. So, in general they are little poorer, but given that they are the same, now we will come out with this F air with these values of 0.495 for y and 1.86 for x. This will be 0.3594, which is less than the previous value, which is 0.3732. So, air system does slightly inferior to the performance of the liquid based system, that is generally attributed as due to rather insufficient stratification or less stratification in the storage medium than what it will be for the air, or the leakages may be a little more, the heat losses may be a little more, consequently hence the load fraction met by the air system for comparable FRUL and FR tau alpha normal in general is lower than that of for the liquid system. So, now let us see if we can improve the heat transfer. Flow rate is doubled. For the air based system. You may recall for the liquid based system, the corrections are for the heat exchanger not being epsilon L C minimum by UAH equal to 2, and the other one is for the storage. For the air based system, the corrections are for the storage and the flow rate, because the performance is highly dependent upon the flow rate for air based systems. So, the correction is now x c by x equal to actual flow rate by standard flow rate. To the power 0.28. So, this will be standard flow rate is 10. So, actual flow rate is 20 to the power 0.28. That will be equal to 1.214. So, the corrected value of x c will be x into 1.214, which will be 2.25. So, this is little unexpected. I will tell you why it is unexpected, and then also I will tell you why it should be expected. So, F is air again 1.04 into y remains the same 0.495 minus 0.065 times x is 2.2, let me check, 25, correct, 2.25 minus 0.159 into 0.495 square plus 0.00187 times 2.25 whole squared minus 0.0095 times 0.495 whole cube. This turns out to be surprisingly 0.337 less than your previous value 0.3594. So, this actually is attributed due to this term with a plus sign, and Xc has increased when the flow rate is doubled to that of the standard flow rate. One reason could be people attribute that at a higher flow rate the storage is very much disturbed. So, stratification is not maintained, consequently the effective temperature goes down, making the effective solar load fraction lower than what it would be at the standard flow rate. So, standard flow rate is sort of a optimum flow rate also, right. So, consequently you have the you can say and that this is less than 0.37 or whatever it is liquid, air at 2 times flow rate. Of course, this liquid is at 125 by 75 storage ratio. Okay. So, this is at a higher storage. So, if you bring down the storage of this, it may be comparable. This is 36 and 37, there may not be much difference between these two. That is what we should not forget. Let us not say in general air system is poorer. No, here this got the benefit because your storage is higher than the standard storage, whereas here this is standard flow rate and standard storage. This depreciation in the performance is because of the flow rate being higher, and that has got its own characteristics as far as air based system is concerned. Now, lastly, this is problem number 10, which should bring us close to these exercises on F chart and phi bar F chart. So, calculate the solar load fraction met by the liquid based obviously or space heating system of problem 7 of 8 etc., using the phi bar comma F chart method. Now, this is a surprising thing. What I have in my mind, phi bar F chart is general irrespective of the system details. T minimum can be specified. I may have a load heat exchanger etc., but if I use the phi bar F chart method and consider T minimum equal to 20 degrees C for space heating, how will this perform? Okay. So, the calculation is a little more involved than the F chart method, but nevertheless the generality of the phi bar F chart method or otherwise can be established. So, we have gone through the steps in problem 6 or 5 whatever, where we were using the phi bar F chart method for calculating the process heating system. So, exactly the same sequence of calculations will be done. So, I would now say design or calculation of solar load fraction by the phi bar comma F chart method. So, I need the non-dimensional critical level first of all, for which I need the critical let me put it down. Okay, critical radiation level, IC, and non-dimensional critical radiation radiation xc bar equal to IC by IT at noon on the average day of the month, and then phi bar max y x dash and then f. Okay. So, this is the sequence in which we proceed. So, out of which the first calculable quantity is this IT noon, for which we need RTN equal to pi by 24 into A plus B cos omega times cos omega minus cos omega s upon sin omega s minus 2 pi omega s by 360 times cos omega s, where A is equal to 0.409 plus 0.5016 sin 73.37 minus 60. Remember that this is omega s, which we have already calculated. This comes to 0.5277. Then B, the constant other 6609 minus 0.4769 sin 73.37 minus 60, the same omega s over here, which will be equal to 0.54795. So, you have got RTN is 22 by 7 into 24 times 5277 plus B is 0.54795 into cos omega, omega is 0, omega because it is the noon time, into 1 to be explicit, times again 1 minus 0.005, omega s is 73, pretty large, cos omega close to pi by 2 I mean, by 0.958 sin omega s, it will be close to 1 minus 0.366. So, this will turn out to be 0.236. Then RDN is pi by 24 times cos omega minus cos omega s by sin omega s minus 2 pi omega s by 360 cos omega s. So, that A plus B cos omega I can easily subtract. That is the advantage of some intermediate calculations, though I have not shown, just divide by that number, you will get 219. So, we got RTN and RDN. Now, Rn, that is the noon time tilt factor, is 1 minus RDN by RTN times Rn 0.749 Hd by H, I am sorry, times 1.82 plus 0.219 by 0.236 into 0.749 into 1 plus cos 50 by 2 plus 0.2 times 1 minus cos 50 by 2. Let me finish, I will explain. I am sure you have a doubt. 1.1627. This is h d by h at k t equal to numerically k t bar. So, this calculation I will show you now. So, R n is 1.1627, but this is where the number of calculations increase. K t bar is h by h 0 bar, h bar is known to us 6.69, h 0 bar is 24 times 3600 by pi GSE times 1 plus 0.033 cos 360 times n is 17 by 365 multiplied by cos phi. This is 284 minus 344. Okay. Cos phi, cos delta, sin omega s plus sin phi, sin delta 2 pi omega s by 360. I think this should be 344. Just check up. I have made the calculation correctly, but here writing is wrong. 2 pi omega s by 360, because this will be the midpoint of the month of December. 2 pi omega s by 360. So, this will turn out to be 16.9 megajoules per meter square day. Or you can look up at the charts in a textbook with a latitude of 35 degrees approximately, it will turn out to be correct. And your k t bar is 6.99 by 16.9, which will be 0.4136. As expected, this is a low value. Okay. So, now h d by h equal to 1.188 plus 2.272 k t, which will be equal to numerically k t bar plus 9.473 k t square minus 21.865 k t cube plus 14.648 k t to the power 4. This comes out to be 0.747. These things I am writing again and again, because if I just say h d by h is equal to 0.747, you may not be knowing which relation I have picked up. So, this is at the expense of little repetition, but then I suppose it is for the clarification, and you will, by the end of the course, you should remember looking at the relation. This is not given to you, this is given to you, you should be able to say, okay, this is h d by h. Now, we also require R b at the noon time. This will be equal to cos phi minus beta, this we have done enough times, times cos delta into cos omega, which is 1, plus sin 34 minus 50 times sin minus 23 by cos phi, cos delta, cos omega plus sin phi, sin delta. So, this comes out to be 1.82. Okay. So, these were the things that we have used in calculating R n. If in the formula 1 minus R d n by R t n times h d by h times R b noon plus R d n by R t n h d by h times 1 plus cos beta by 2 plus 0.2 times 1 minus cos 50 by 2. This comes to 1.1627, and your R bar is h t bar by h bar equal to 8.69 by 6.99 equal to 1.2432. So, remember this we calculated in problem number 7 or 8. Okay. So, now R bar by R n, the ratio required in calculating the monthly average daily utilizability, turns out to be 1.0692. So, we calculated one of the things required. Then we will go ahead with IC, the critical radiation level 2.63 FRUL into T minimum is now 20 minus T ambient is 2.8 times 3600 the time factor, not to be forgotten, by 0.72 into 0.94. So, this will be equal to 0.240617 megajoules per meter squared hour. The non-dimensional critical level will be I c by I t n, which will be 0.240617 by R t n R n into h bar. R t n R n h bar. Okay. So, this is in megajoules, this is also in megajoules, no problem. This is equal to 0.12544. So, this is another thing that we require in the phi bar F chart method. Okay. Now, phi bar max will be exponential to the power a plus b times R n by R bar times x c bar plus c x c bar square, right. So, a the constants are 2.943 minus 9.271 kT bar plus 4.031 kT bar square. So, this will be kT bar is 0.41 something, which we have already kT equal to kT bar somewhere we have written. Point 4136. Okay, I can write it here. Okay, So, this is minus 0.2019, B is minus 4.345 plus 8.853 kT bar minus 3.602 kT bar square. This will be equal to minus 1.29. Then C, you can calculate it, or whatever is the formula, that turns out to be 0.205. So, phi bar max e to the power minus 0.2019 minus 1.29, that is this, into Rn by R bar, which will be 0.935. This is Rn by R bar, which is 1 by R bar by Rn, which we have calculated earlier, times C Xc bar 12544 plus 0.205 into 0.125 square. So, this will be 0.835. So, the utilizability is pretty high, right. The reason is it is operating at a T minimum of 20 degrees, considerably lower than for the process heating system that we were using earlier, which was at 60 C. And particularly there are logic to say that non-dimensional utilizability phi bar will be higher at lower kT bar. This is not to imply that there is a solar radiation received is higher at a lower kT or any such thing. The non-dimensional value of phi bar is higher at a lower kT bar. That comes from the non-uniformity of the clearness index, or the non-uniformity of the solar radiation, more non-uniformity if kT bar is lower. Now, I need y equal to 0.495 from the previous problem. And now, I need x dashed. You can write of course as f or UL into 100 into AC into delta tau by L, which will turn out to be our previous x multiplied by 100, because that is this 100 by 100 minus T A bar, because x contains this 100 minus T A bar. It is a simpler way, since we already made calculation. 1.86 into 100 by 97.2, this is 2.8. So, this will be 1.913. So, now we got y, we got x dashed. So, we are all set to calculate the solar load fraction. F is equal to phi bar max y minus 0.015 e to the power 3.85 f minus 1 multiplied by 1 minus e to the power minus 15 x dashed times RS to the power 0.76. So, standard storage, so RS is equal to 1, and first we are calculating no heat exchanger, no tank losses. So, F will be phi bar max is 0.835 times y 0.495 minus 0.015 into implicit e to the power 3.85 f minus 1 multiplied by 1 minus e to the power minus 0.15 x dashed into 1.913, right. X dashed is 1.913, that is correct, times 1, that is the standard storage to actual storage ratio. So, this F will be 0.4133 minus 0.00375 times e to the power 3.85 F minus 1. Okay. So, this will be, that is right. We will start with a guess of F. Let us take it as 0.38, because we calculated by the F chart. If it is to be close, it could be 0.438 and should be less than 0.4133. So, it justifies that I will choose some value like 0.38. That is equal to 0.4133 minus 0.00375 times, this is you put a that 3.85 into 0.38, that will turn out to be 3.19 minus 1, which will be 2.19, equal to 0.4133 minus 0.008, that is 0.405. So, this is close, but not as good as it can be. We can simply, so somewhere it should be lying in between these two values, because if I increase this, it will decrease, but at the same time if we increase equal to 405, the number will be less than that. So, I will choose, next guess will be 0.4, that will give me phi bar max by 0.495, that is 0.4133 minus 0.00375 times, this is 3.66 minus 1, which is 0.4133 minus 0.0137. So, left hand side will be 0.4 and the right hand side will be 0.39955, pretty close. So, you got F of 0.4 for standard storage, no tank loss, and infinite heat exchanger by the phi bar F chart method for the same split sitting system. This is about 0.37 by the F chart method. Even these values we might say, can say that they are comparable, and if we want to be very particular, or calculate tank losses and Hx effect on the phi bar F chart calculation, right. So, obviously, if tank losses are included, and a finite heat exchanger is considered, F from phi bar F chart method will be less than 0.4, goes close to 0.37. Of course, 0.37 also is slightly inflated because the storage is higher. We can do the same thing for the F chart method also. So, these values are quite comparable. So, about 10 examples we have solved to illustrate the calculation of the phi bar F chart method to obtain solar load fraction, then how to include the tank losses, then subsequently include the effect of the heat exchanger. Then we considered a equivalent space heating system for the Indian location of Srinagar, obtained by an approximate method, the degree days, which coincided with the actual calculation. The reason being, no time the temperature is higher than the minimum comfort temperature of 20 C or 19 C. Consequently, this calculation helps is accurate. And then we use the F chart, both air based as well as liquid based, to calculate the solar load fraction, and studied the effect of the non-standard storage and non-standard flow rate for air collectors. And we found that the performance in general is comparable. However, the air based systems perform slightly inferior to that of the liquid based systems, and in addition to higher pumping or power requirements. Subsequently, we took a exercise, how would the phi bar F chart method be to design the space heating system or to calculate the solar load fraction for space heating system. So, apart from the intricate details, differences in the details of the system configuration, you have a T minimum requirement of 20 degrees C in the case of space heating system. So, I shall use the phi bar F chart method, assigning T minimum to be 20 C. We carried out that exercise, calculating the corresponding critical level, corresponding non-dimensional critical level, and the monthly average daily utilizability, and through an iterative process the solar load fraction, which came out to be 0.4 compared to 0.37 for the air based system, and this 0.4 is without considering the tank losses and assuming an infinite heat exchanger. Consequently, if these losses are included and heat exchanger effect is taken into account, phi bar and F chart, at least for the example we have considered, are very close. And with experience, I can tell you, I made quite a few such calculations. One can be interchangeably used. In other words, phi bar F chart can be used for the liquid based F chart for space heating or domestic hot water, but they are not the other way around. You can't get the process heating results from the F chart method. And of course, the equivalence of a air based system by phi bar F chart method is not available. This is the sum and substance of the design methods, which you have to make 12 monthly calculations. However, even for a yearly prediction by hand calculation, it is a tough situation. So, one would go for a little programming, but then once it is done, it is quite easy to calculate the yearly solar load fraction. That is, ultimately by making 12 monthly calculations, we are in a position to get area versus solar load fraction, something like this. This is unity, and I can do whatever optimization or whatever studies one like to have by changing the system parameters, either the storage or the flow rate or the heat exchanger size, location, area of course is the main thing, and collector parameters. Okay. So, we will talk little more about the collector performance parameters and their influence on the parameters when we talk about little bit of economics in the next lecture. Thank you.